Okay, hello everyone. Welcome to the week 10 of problem solving session for the NPTEL course. So, yeah. So, the topics for today would be the counting class Sharpie and yeah, pretty much about this complexity class and just want to clarify one thing that we were discussing last time. So, um, okay, we made this claim here that uh, yeah, that all languages that are in p/poly are sparse sets. So and then we were wondering whether sigma star is a counter example to this. So actually this claim as it is not true. That's why we had a counter example. But there's a small modification to it that makes it true. Um, the actual claim is that any language that is in p/poly has a um, has a Cook-Levin reduction to some sparse set. So L star by itself, uh, L star by itself is not sparse, but it is enough to say that it is Cook-Levin reducible to some sparse set. That would be enough. So that would make our whole counter example fail. And this claim turns out is true. Will not prove it, but just want to make this correction. So okay. Okay. So yeah. So we'll move on to the. So I think we did discuss briefly about this class earlier, but we'll go into it in a bit depth this time. So how do we define Sharpie? We have the decision world, which is we have the languages P here, NP here, um, EXP, or let's say I'll just do P space for now, P space and so on. Similarly, we have a counting world here where, for example, in NP we ask questions like given a graph G, um, comma K, output yes if there is a click or size K. And the counting counterpart would be that the input to us is a G comma K and output is the number of K clicks in G. So this is a much stronger question because of course if we have answer to this, we definitely have answer to this, because if you have the number of K clicks, just check whether it's greater than 0. If it's greater than 0, then say yes. If it's not, then say no. So this is clearly more difficult than the NP counterpart. So also notice that the way we define these questions here, these were all decision problems. They're only allowed to communicate one bit, which is either a yes or a no. Whereas here the answer could be a binary string. So we need to define our model accordingly. So okay, so the counterpart of P here is what is called FP, where it is a set of all functions that have a deterministic machine that will finally write the output of f of x. Given input x, it will output f of x for that particular input on the tape. So this is not necessarily a 1-bit string, but rather it's a binary. It could be a longer string. Okay, it can't be, although we have written sigma star, it really can't be very long because the algorithm itself runs in polynomial time, so it will not even have time to write more than polynomially many bits on the output tape. But anyway, I mean, it follows from the semantics, but I'll not write it for now. But yeah, this cannot be really large because of the time constraints it has. So now, what is a um, counterpart of NP in the counting world here? So,
So I have a query here
hmm,
that what kind of function this small f here is. Because in the counting world, we would only be interested uh, in writing functions wherein we would be counting the solutions.
hmm.
And now seems that as if here we are transforming the input x into something else. So what kind of function this f is?
So f is a function from sigma star to sigma star. Okay, and this is our input, which could be, um, let's say a graph G. Okay, and um, I mean, I'll just take a very simple problem for now. So uh, matching is hard. Vertex cover even cycles is hard. So um, okay.
Like say
Hmm.
in the minimum spanning tree which we can solve in the polynomial time,
Hmm.
and if we can find that how many different MSTs are possible, probably that would
Yes.
belong to count kind of.
Hmm. Yeah.
So can we understand this f function through this example of the MST? In fact, what is not clear to me is that it's okay that the input is x, but then since this fp is the counting analog of the p complexity class in the diffusion world, as you said, so this fx here is transforming this x, and it is not giving. I mean, it is not giving an impression of counting the things. So that is the problem.
Mm, okay, so this thing here is a binary string, right? So sigma for us is 0 1. So this is nothing but 0 1 star. So what this machine will basically do is it will look at this x and um, do some computations, but at the end of the day, there is an output tape where it will write f of x, and f of x is nothing but, I mean, this is like any other Turing machine where it does some computation, writes something, but the final thing that it writes on the output tape is what we will interpret as a number.
Right, right. Yes, I understood you.
Yeah.
And this number would basically be a count of something, and I mean,
Yes, yes.
yes, and the
That will
problem.
be the value of
Yes, I
f of
understood
x.
you. Thanks. Yeah,
Good. Yeah.
thanks.
Okay. So, hmm. Okay. So then, the analog that we have for NP here is what is called sharp P or counting P. And how do we define that? So notice that we say that a language is in NP if in the computation tree there is at least um, so if x is in L, then there exists one accepting path. So if you look at the computation tree of x, and these are all the paths that it leads to, if at least one of them is accepting, we're going to accept, and the only case that we will reject, so we can just combine this here. Okay, and in the case of reject, all the paths should say reject. Okay, and now what the sharp P says is that a language is in sharp P if there exists a non-deterministic Turing machine M um, whose such that, so this is a function actually, 0 1 star to 0 1 star. So okay, if for all x the number of accepting paths of m on x is equal to f of x. Okay, so earlier it was sufficient to have one accepting path for a string to be in L, but now for that text we want exactly f of x many accepting paths in the Turing machine, um, for all x. And okay, so for example, if we are talking about sharp SAT, where this is the number of so given a fee, formula fee, count the number of satisfying assignments of fee. Okay, so now what you want is that um, for any formula that I give, it should have, so let's say it has k many satisfying assignments, then the number of accepting paths in the non-deterministic Turing machine should be exactly k.
Yes. So
Okay.
can we think of like the co version of this Sharpie, like say something like we have Go and P, and then do we have something like say what would be the interpretation of then Co Sharpie?
Hmm. Good. That is a good question. So, yeah. So notice that the if let's say we define co-Sharpie similarly, that um, so it is the set of all functions.
Whose complement is there in Sharpie?
Huh. As in if so for all x in 0 1 star, the number of accepting paths of okay, there exists a non-deterministic Turing machine M such that the number of accepting paths of M, or we should say rejecting paths of M on X, is equal to f of x.
Okay.
Okay,
Yes.
so okay, so notice this class will coincide exactly with Sharpie, because if f is in Sharpie, let's say, then there's a non-deterministic machine M such that f of x is equal to the number of um, accepting paths of M on X. Okay, now what you have to show is that can you somehow convert this into another non-deterministic machine M prime such that f of x is exactly equal to number of rejecting paths of M prime on X. So if we could do this, then that would mean that f is also in co-Sharpie.
Yes.
So can we do like a small change to M to get the sampling?
Uh, yes, then from the machine name and wherein we are having the count of the accepting path is equal to something. And if I want to say, say like the number of the accepting paths is equal to accepting path is equal to say k,
Hmm.
and if I want to make it say co-NP, wherein the rejecting path, say in the case of the in the case of m, the rejecting path is equal to say n minus k,
Hmm.
and I want to make it k
Hmm.
for the machine n. So what will I do?
Hmm.
I can add some dummy paths and which will always lead to the rejection just to increase the count or decrease the counts.
If
That
you
can always
add
be done.
if you add parts, you can increase the count if you want. But if you want to decrease the count,
So in case if I want to decrease the count, then also uh, yes. So then if I want to decrease the path that which are leading to the rejection, and if I want to reduce those paths, uh, so I'm not unable to think straightly, but uh,
hmm,
so like say, but then how many paths? Say if satisfiability is in Sharpie, that would, or if the Sharpie I mean version of the satisfiability, the problem formulation would be like this: that this satisfiability instance has k number of the satisfying
unsatisfiable.
yes, satisfying assignment. So this will vary from so then this would be the collection of all the Boolean expressions and which have got k or more number of k or more number of the satisfying assignment or exactly k number of the satisfying assignments.
Hmm. So here actually, you have two. Um, I mean, hmm. Here you have two parameters. So you can think of this as the set of all phi comma k, such that phi comma k such that the number of satisfying assignments of phi is equal to k.
How will this affect the complexity of the solution? If instead of saying that I am looking for this exact value k, if I allow that the number of the satisfying assignment are less than or equals to k or greater than or equals to k, because if I give an interval, then probably it would be easy for me to find, and instead of knowing that we have this, I mean, satisfying assignment equal to a particular quantity.
Even if you define it to be at most k, the problem will turn out to be, I mean, it will not make the problem any easier.
Okay,
mm,
okay, okay. Okay, I understood. Yeah, makes sense. So now in the
so
case of this co-sharpie, if I am looking for, if I want to reduce or increase the number of the rejecting paths, the number of the rejecting paths probably, but then I can make modifications in the Turing machine. But how to reduce the number of the rejecting paths, that is an issue. Increase can be done, and so how to reduce so I can use some negations, some negators, that whenever say I get the rejections from these number of the outputs, then I will just negate them.
hmm, yeah. So so let's say that we have this m, and we know that the number of accepting parts here, let's say f of x is k. So there are some k many accepting parts here. So this is accept, 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 k many of them, and rest everything is reject. Okay. So now we want another machine So this is for m, and for m prime we want that, let's say the paths are entirely same, and the only change that we are going to make is, let's say, here, I mean, in this case this is sufficient, although we can, like you said, extend the paths and so on. That is a possibility, but in this case we don't even need that. So what I want is, we want let's say the k of them to be rejecting, and the remaining everything to be accepting, because that would satisfy our constraint that there are k many accepting paths. So what this machine can do is, m prime, it simulates m. Whenever m accepts, it rejects, and whenever it rejects, it accepts. So you will have exactly k many r's here, and the rest all will be accept paths.
Yes.
Okay, so what m prime does is, sorry, so m prime, what it does is runs m on x. If m accepts, then reject, and if m rejects, then accept. Okay, so therefore we have that number of accepting paths of m on x is equal to number of rejecting paths of m prime on x, and this is nothing but f of x. So this is nothing but f of x, and this shows one direction, that is, if f is in sharp p, then f is also in co-sharp p, but the other way. So therefore this shows that sharp p is contained in co-sharp p, and the other way around can also be shown, right? So if you have a machine for co-sharp p, then you also have a machine for sharp p.
Yes, this is true.
That is exactly the same argument. So similarly it can be shown that so therefore sharp p and co-sharp p, they are exactly the same. So
Yes.
okay, good. Now one thing is, when we defined NP, there were two definitions that we had. One was with respect to this computation tree, that if one of them accepts, then we should accept, and if all of them reject, then we should reject. So there's also one more definition that we know, which is based on the verifier. So there's a small certificate which is easy to verify. If that exists, then the language is in NP, and if that does not exist, then the language is not. So alternatively, we have a verifier based definition of NP, which is L is in NP, then X is in L. Just call it B for now. B of xy is equal to 1. Okay, so this is the
Would it be DTM or NTM? P directly.
so this is a certificate that we are guessing, So after that, we should
Yeah.
verify in deterministic polynomial type
Yes,
theory.
yes, yes, right. Yes, that's all.
Okay. So, a similar definition of equivalent definition of sharp P would be that so hmm, sorry. So here we are saying that there is some certificate um, for B that will make it accept if the X is actually in L. Otherwise, no certificate that you give will make it accept. So similarly, we want to capture the fact that the number of such certificates Y that you have should be exactly equal to f of x. Similar to the fact that here you just wanted one satisfying assignment, but here you want f of x to be equal to the number of satisfying assignment.
Yes, yes.
So b of x comma y. Mm, so this need not be in FP actually. Uh, yeah, that should be fine. Yeah. And also y is here polynomially bounded. Will not. I'm not writing it though. Okay, so these are yeah, the equivalent definition of Sharpie, which sometimes one is more useful than the other. Okay. Also, um, also, uh, yeah. So by the um, yeah, this proof that we did just now, what this also says is that Sharpie is closed under complementation.
Yes, yes, sharp is close to it. Right.
So, okay.
So A is an element of NP, and this would imply that the sharp A of is an element of the sharp P. So okay, so if a problem, and then what would be the meaning of the sharp P? Sorry, sharp A.
Sharpie. So, um, yeah. So, it's basically the number of okay. How I mean in general. So, I can easily explain with example. So, for example, if A is sat, Sharpie is the number of satisfying assignments. If A is the click problem, Sharpie is the number of clicks.
Yes. Right. Now I understood. I mean, basically the count of solutions. Right. So in the case of A, we would be getting the yes and no kind of the thing that belongs to NP. And then in the sharp A, we would be counting the number
The
of
number
yes
of
or no.
witnesses.
No.
The number of
Right.
certificates.
Yes. So that would belong to that would be the element of the sharp P for sure according to the definition which you gave just now. And A is the element of the co P, then this would imply yes just now I mean based on the argument. So since I mean, we can always design the Turing machine, the description you gave. So both are true.
Yeah. So this is true because if A is in NP, then we had this machine where the number of yeah, where you had several accept and rejects, and for this machine itself, the number of accepting parts corresponds to the number of witness it has, or even uh, with respect to this definition, it's uh, yeah, it's clear that the number of certificates is basically the answer to the to the function that is in sharp. So with both definitions, one is true, uh, and we also saw that by the same argument, if A is in co-NP, then sharp A would be in co-sharp P. But we just saw that this class is same as sharp P, so therefore sharp A is in sharp A is in sharp P. Okay, good. So this is
So are all are there decision problems in P whose counting version uh, is uh, is sharp P complete?
hmm. So
So
before this, I'll just sorry, I should have talked about this first. So I'll just draw this class. Okay, we'll get back to the question. Just a minute. So we had this. We said that this NP corresponds to the sharp P. It's an analog in the counting world. We have P sitting here, and we also have FP here because this is the class of functions whose computation can be done by a deterministic polynomial machine. So,
yes.
so clearly by definition, it lies here. And similarly, there are these other analogs here. So for P space here, you would have FP space and so on. Similarly, you had sigma 1 here, sorry, sigma 2 here, which is um, okay, this okay. It's not exactly sigma, but okay. Let's say you have P to the NP here. Okay, this is a class here, and of course, above, even above NP, this is the set of all problems that become decidable. If given access to NP Oracle, you can similarly define um, FP to the FP to the sharp P here. Even FP to the NP is well defined because you can still give access to decision problems, and the result that your base machine is computing is still a value of f(x). The only thing is, in its computation, it may use Oracle access to some decision problem. That is still fine. Uh,
Yes, but then what would this space complexity class FP space mean?
FP spaces, uh, the set of all deterministic, sorry, languages that have deterministic Turing machine, and they're going to compute the value of f of x at the end. Similar to this, they are going to write this on the output tape, but the amount of space they are allowed to use in the work tape, that is bounded by polynomial.
And do we have the same relationship in between the Sharpie and the FP space, which we were having in between
Yes,
NP and the
yes,
P space?
yes. Actually, the same proof, it turns
Okay.
out it follows. So a lot of relations are exactly captured because the same proof works most of the cases.
Including the Savage's theorem, wherein the P space is same as the NP space. So do we have such equivalence for this FP
So,
space?
um, okay, so FL is something that is not very much studied. So I've not seen it anywhere. So, hmm. So I'm not sure whether the same proof will go through. Mm,
So which complexity class you said for the space thing and the non-deterministic one? Uh, so what was the name you just said? I mean for the non deterministic. equivalent of this FP space? What is the name of the complexity?
Oh, sorry. Sorry. I thought you were asking about the L.
No, I was not asking
Hmm.
about L. I was asking about this non-deterministic equivalent of this FP space. And this
Okay.
L will
Okay,
also come
okay,
into the
okay.
picture. Yeah,
Okay,
L
okay.
and
Hmm.
Z. Yeah.
So here you know that P space is same as NP space.
Yeah.
Hmm. So it also happens that the non-deterministic counterpart here is the same as FP space. So we just call it FP space.
Oh, you
Hmm.
don't have anything like say FN space kind of thing, or
Hmm.
FNB space kind of thing. Okay, cool. Yeah.
But there does exist a class called FNP, which is different from sharp P.
Oh, okay. So there is one FNB as well,
Hmm.
right? Um, but then,
But
yeah.
hmm.
So where would the difference be in between this FNP and then Sharpie? Because I thought that the name of the FNP has
Hmm.
been done as Sharpie only.
Okay. So the sharp P, um, hmm. So the sharp P has this condition that the number of accepting paths should be equal to the value of f of x.
Right.
Right. And what FNP does is just that it's same as FP, where only difference is instead of deterministic machine, it's allowed to use non-deterministic machine. As in, given x, it will compute the value of f of x on the output tape, but the machine that's running is not necessary. I mean, can be non-deterministic. So here it computes the value of f of x explicitly, writes it on the tape using a non-deterministic machine computation, whereas for this the number of accepting paths of the non-deterministic machine should be equal to f of x.
But then whatever value the f of x, this FNP would be writing there over the tape, in fact is equal to the k only. I mean, because in this example, given just below, wherein the x was getting transformed into the fx, right? So this fx used to keep the count on.
But there's a difference between writing computing a value and writing it on the tape and having the number of accepting paths as. So for example, this non-deterministic machine may have only one accepting path. Okay.
Mm.
But in that accepting path, I mean, uh, what it does is it does compute the correct value of f of x, which may be different from the number of accepting paths.
Um, it is not well understood. But this difference, I cannot understand this diagram. So what was
Okay.
the argument here that if the Turing machine is accepting through one path, because if Turing machine, if this FNP is printing, say f of x there over the tape,
Hmm.
and f of x somehow is representing, is having, is imbibing that count thing within itself.
So
Let's say this now in this example, say fx is 0 1 0 and then 0 1 0. So it should have something related to the count thing. That is why this is FP. You
so
said.
this count is related to the f that we have. So for example, if um, let's say this is the satisfiability function where given v you have to count the number of satisfying assignment. So what FNP expects you to do is to write the value of that k here. Okay. But the machine that it is using to compute this, right, to do this entire computation and come up with this value, need not have k many accepting paths.
Okay. Okay. So, but then you said that in the Sharpie, there would be, I mean, in this verifying analog of the NP, as a verifying analog of the NP.
Hmm.
In the case of the Sharpie,
Hmm.
I mean, it used to be and there has to be k number of the accepting paths.
Hmm.
So if there are k number of the accepting paths, then whatever this Turing machine NTM is writing there over the tape,
Hmm.
its equivalent value should be same as the number of accepting paths, isn't it? Because this value is also representing a count, uh, some sort of the count. And there also, like in the case of the satisfiability problem,
Hmm.
so if we are using a NTM and then I give a formula. So now this NTM is no longer going to tell me that whether this Boolean expression is satisfiable or not. It will say that okay, instead of telling you, so I will write say one in the beginning, and that one will show that the Boolean expression is satisfiable. And after one, I will write a binary string say 0010, and that will give me that not only this expression is satisfiable, but it has got two satisfying assignments. So initial bit would be 1 or 0, like say whether the expression is satisfiable or not, and the remaining string would give the count of the satisfying assignment. Then it makes sense that this of this FP or the FNP complexity class. And similar thing can easily be translated into the Sharpie, wherein if I design the Turing machine, then there would be a number of them, isn't it?
Mm, okay. So, um, okay.
So basically,
So,
what is not clear here is that while defining this FP class itself,
hmm.
what this function f used to be, because I understood it like
Hmm.
this f is transforming x, and whatever this fx value is, this represents some form of the count.
Hmm. Yeah, yeah. So, yeah. So, uh, the value that's there. So, for example, if this is sat, the f of x is still the number of satisfying assignments.
Yes,
Okay. The only difference is here you are expected to just compute that value and write it on the tape.
yes.
Whereas here the number of accepting paths that you must have uh, should be equal to f of x. So it should be equal to the number of satisfying assignments. So it may happen that you are able to compute the number of satisfying assignments, but your total number of accepting paths may not be the same number. That is fine.
It should be same. It should be same. I mean, if my if the conceptual understanding is fine. Why so? Because in the definition itself, you said that there would be k number of the satisfying set. So the value of f of
The
x is k.
definition of
That definition of the
Sharpie. Right,
Sharpie.
right.
You said that there exists a deterministic Turing machine B, and such that the count of the certificates Y
Hmm.
would be equals to k.
Yeah.
For k number of the certificate, the DTM would
Hmm.
be generating a 1.
Hmm.
So if that is the case, so for k number of the certificates, it would be generating a 1. And now
It would be
what
generating.
DTM B would be generating a 1 for exactly k number of the certificates Y. In the
Uh,
definition you said where, while defining this Sharpie as an
what do you
equivalence of the
so
verifying machine.
so what do you mean by generating a one? Because so this is a
Yes.
deterministic machine. It will accept or reject. So
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 same thing.
for
I mean, when I use the term generates, I mean to say that yes. I mean, it would say yes.
huh
So
okay.
this DTM would say yes
Huh.
for Y number of the
For
certificates.
k many f of x many certificates.
Yes. That's right. So probably there is some language issue in the difference in between FNP and the Sharpie, which I am missing, because I view it like say f of x is equal to k.
So
I mean,
hmm.
whatever the NTM is writing there over the tape, its decimal equivalent or its binary equivalent, whatever. I mean, something is equal
Hmm.
to
Hmm.
k.
Hmm.
And according to this definition, then I would be having k number of the accepting paths.
Hmm.
So in a sense that I view that as if the FNP and the sharp P is one and the same.
Okay, so let me just write the two definitions. So if I come up with a good example, that would be nice. Okay, I'll think of it just a second. Let me write the two definitions side by side. So this is also with respect to the deterministic. This is with respect to the deterministic machine. So if F is in FNP, there exists a non-deterministic Turing machine N. Uh, hmm, I mean, this runs in polytime. N such that um, for all x n okay.
So should we compare these two definitions then?
So I think uh, it would be nicer if we could come up with some example that shows um, I mean something in FNP, something in Sharpie, and then show the difference. So let me just think of something. Mm, so I'm just thinking if cycles. Hmm. Hmm. So although I don't have an example, let me just try to convey something. So let's look at sharp sat. Okay, and we know that sharp sat is in Sharpie because uh, yeah, because the number of um, satisfying assignments, so basically the same machine that we have where the number of accepting paths corresponds to the number of satisfying assignments
Yes.
exactly computes. But let's say you want to show that sharp sat is in FNP.
So if sharp set is in FNP,
Hmm.
then I would be showing that there exists a Turing machine
Hmm.
such that when I give an instance of the satisfiability to this NTM,
Hmm.
then the NTM will not only say yes, but it will compute something, and that something
Compute
is
the
f of
number of
x.
it's the same thing, yeah, computes the number of satisfying assignments.
Yes, yes.
So how do we do this? Because although for the machine that yeah, so we know that there is a machine n such that for every formula phi, the number of satisfying accept paths is equal to the number of satisfying assignment, and the rest of them are all rejects. Okay, so even though I know that, that is not enough, because what this requires us to do is to explicitly compute this f of x and write it on the tape, right? So this value, whatever it is, I want to write it on the tape. So um, yeah, I mean, do you agree with this?
Um, not really, because if x is if there exists n, and this n is giving satisfying assignment for, I mean, is having k number of the accepting paths,
Hmm.
and if I give x, and if I make a slight modification on the tape, that I am having two tapes, one is work tape and one is the output tape,
Hmm.
and then probably I will only count the things which are I'm going to count only those computations which are going to make over the work tape, and I have displayed this value k over the output tape, and but then how will it make uh, the entire thing different from the sharp view? This is
Huh.
simply sharp view.
So, but I mean, you do agree that for F to be in for sharp SAT to be in FNP, there should be a non-deterministic machine that will compute f of x and write it here, right? That
Right.
means,
Yes. Yes.
so
Yes.
now what I'm saying is, it's hard to show that sharp SAT is in FNP, because although the number of accepting paths that this machine has is equal to the number of satisfying assignment, I really need to write that count. Now the problem that we will run into is that I can't count this explicitly, because this is the computation tree, which could be really large,
I
exponentially large. Huh?
yes, I understood. I understood this thing because once we start from a configuration and I reach to the accepting configuration, there is no way to go back and then find that how many paths are leading to the accepting thing.
Or
That's
even if you do like a breadth-first thing and try to compute it parallelly, what will happen is this will take so much time that we don't, I mean, because each of these is polynomial length, and altogether this could be exponentially many. So we don't even have that much time, because we only have a non-deterministic polynomial time machine.
right. Yes,
Right.
I understood the difference. Yeah, thanks. Thanks.
Yeah.
Yeah.
Okay. Good. So, hmm. Okay. Although, okay, fine. Why did we come here? I'm just trying to recall that. Okay. So we were here, and yeah, we saw. Sorry. Hmm. So we saw this hierarchy and this hierarchy, and then there are several classes here. Hmm.
Yes.
Okay.
Yes.
So we were drawing this picture. Okay, got it. So, hmm. Yeah. So there is this hierarchy here, similar to this. I mean, a lot of it is kind of same. It gets complicated if you go down this down to L and so on. So that is anyway not explored. So we'll not get there. But recall that there's a notion of hard problems here. So, hmm. So you have NP complete problems. And yeah, again, similar to the P versus NP question, we have whether P is equal to NP, we have the question of whether sharp P is equal to FP, or whether FNP is equal to FP. And we also did these implications that sharp P is equal to P, then F is equal to FP, then P is equal to NP. So an answer here would give us an answer here. Okay. Anyway, so
I have a query here that where does this FNP fit in this diagram? So where to fit FNP? FNP, I mean, does this mean that FP is a subset of the FNP? And
yes,
FNP probably would be the subset of the sharp P, and we do not know the boundaries.
so like the picture that we drew, FP is here, FNP is here, sharp is here. Um, yeah, we don't know. Okay, at least as far as I recall, we don't know. But I should. check this again, the FNP versus sharp P thing.
Okay, okay.
Okay, so yeah, so we have this kind of an implication, therefore this is an interesting problem in itself. Okay, and yeah, and now we have this notion of the hardest problems in NP, which we call the NP complete problem. So similarly, is there a notion of hardest problems in sharp P, so which we can call sharp P complete problems. And why do we need that? For the same reason that we needed uh, the NP complete problems, that can there be one problem which captures the hardness of the entire class, so that now that I know that, let's say, SAT is hard, what I'll do is I'll just try to design algorithms for SAT. If I do get a polynomial time algorithm for SAT, I would have proved that NP is equal to P. Okay. Similarly, this captures is can be captured like one problem uh, that's the hardest among the Sharpie class, so that if I can develop an FP algorithm for it, then we would know that Sharpie is equal to FP, and therefore we would know that P is equal to NP. So turns out that sharp SAT is a Sharpie complete problem. Now, um, when we define the notion of completeness, we should always be careful about what is the notion of reduction. So, when we say that a language is NP complete, we say that L is in NP, and for all A in L, sorry, A in NP, there's a polynomial time many-one reduction from A to L. Okay. Similarly, when you say that a language L or a function F is in Sharpie complete, first thing is of course that F should be in Sharpie itself. But the more important thing is, how do we define this notion of reduction? Because we can't say that for all G in Sharpie, G reduces polynomial time many one to F, because this does not make sense. Here, these are decision problems. So we know that we had this notion of a sigma from what I'll call it a phi. What this does is that it takes an input of x, gives us a phi of x, such that x is in A if and only if phi of x is in L. This is the, and also phi should be efficiently computable, this should be polynomial time computable. But this was the kind of reductions that we said, that there is some transformation that we can do to inputs of A and get our inputs of L and solve it for L, and based on that we will get back our solution for E. But these were decision problems, therefore saying that L accepts, then A accepts, and L rejects, then A rejects, that makes sense. But these are functions here, so this does not make any sense, like even converting one function to the other function. And these are functions in the first place. So G is some sigma star to sigma star by itself, and F is also sigma star to sigma star. So converting one function to the other itself is a bit tricky to say, and then transferring the solution back also. So this,
Why functions here and why not languages here? Because
because
whichever languages are there in this counting complexity class, are they viewed
are
as
they
a
all
function of?
functions? Yes, exactly. So all the definitions that we defined, um, yeah, yeah. So all the definitions that we defined were with respect to functions. So f here and so on, right? F of x and so on, that we were computing. Even, yeah,
Yes, yes, yes. Right.
even sharp sat is a function from the formula to the number of satisfying assignments.
Yes, even what did you say? Like I could not hear it properly. That
Huh.
even in the sharp shift.
It is a function from the formula phi to the number of satisfying assignments.
Yes, fine. I understood.
Yeah.
Thanks.
Okay. So yeah, so that's why the F here basically stands for functional P, functional NP, and so on. Okay. So hmm, where were we? Yeah. So these are all functions from 01 star to 01 star, and so is G. So yeah. Okay. So therefore this really does not make sense to like carry forward the same notion of reduction because we have functions here. So what do? We define it. One second. So we define it in the following way. We say that for all G that are there in sharp P, if I can find the value of G using oracle access to F as a function, okay, then we'll say that it is that G is sorry, I did the other way around. Uh, no, this is fine. Yeah. So that would mean that F is hard because all the other problems that are in Sharpie are solvable in FP given access to F.
Uh, so, like in the case of the NP completeness, all the problems which are there into NP are
Hmm.
getting reduced into this problem L. So, yes, and similarly here,
Hmm.
if you want to show that F is an element of the Sharpie complete, then F itself is the element of the Sharpie, and all those problems which are there in Sharpie can be reduced into this problem F, into this function F, say for example.
Hmm.
So, then you wrote that for all G's, which are the elements of this thing, all the G's can be reduced into, makes sense, FP and with an oracle of F. So this FP part is okay. FP part is okay that we are computing the value of the f of x using the deterministic Turing machine,
Hmm.
probably just to reduce the, just to show the reduction here, and then we are giving an oracle access of f. So what would it mean that if I have a DTM with an oracle access of f, then I should be able to compute the g of x in
Hmm.
the polynomial time.
Hmm.
It's the same thing. Yes, I
Yeah.
understood this. Yeah, thanks.
Yeah. The
Right.
kind of queries that you will make here is you will send an x and it will tell us the value of f of x. Using that, we will compute the value of g of x. I mean, g of y, some other.
Yes, right. Yes.
Okay. So it turns out that this also replicates a lot of, um, a lot of theory that we developed for the NP completeness. For example, the story for these problems where we first discovered that 3 sat is hardest, then we did a 3 sat to vertex cover reduction. So we did 3 sat reduces to vertex cover, therefore vertex cover is also NP hard. We have vertex cover to independent set to click, and so on, right? We have many of them. Turns out that similar to the fact that sat is sharply complete, we also have sharp vertex cover is sharply complete, sharp independent set, and so on. All these are sharply complete problems. And how do you show that? Actually, at most of the places, at least for these four, the same reduction works in this with respect to this notion also. So it's actually, it's a nice exercise to try out. So maybe since these two reductions are easier, you can try to use the same reduction idea but with respect to this notion. and show that, for example, um, assuming that we know vertex cover is complete, sharp vertex cover is complete, try to show that sharp independent set is complete. So, um, yeah, just leave it with that. Um, okay.
Uh,
Hmm.
doesn't like to because independent set is the click to for getting the click of the graph to see that of getting the independent set of the inverse graph.
Huh. So let's try to do that. So how do we do independent set to click? So the input to us is a g comma k, and you want to check whether g has a k sized independent set. And here we observe that you take the complement of the graph, then any two vertices that did not have an edge will now have an edge here in G bar, and any two vertices that had an edge will now not have an edge in G complement. So basically, if you look at an independent set here, no two of them have an edge, that would transfer to a click here.
Yes, it's okay. So now if I have availability of the vertex cover, say now if I have an availability of the f function and which corresponds to the vertex cover.
F corresponds.
So yes. So
Uh,
f is available. F function is 4. So since this vertex cover, sorry, this independent set
hmm,
is an element of the Sharpie.
hmm.
So therefore, this
So,
let us call this as f. So f
so
corresponds
what
to
this
the
does is counts
uh,
the
yes, counts the number of the independent sets
of size k.
of size k, and then g would be another function, and that will count the number of the clicks of the size k
Hmm.
for the inverse graph, right? And now the thing is that can I find a deterministic Turing machine uh, to whom when I give when I give any instance of the click problem, and if I have an access to the to this independent set function, I mean
Hmm.
I have an availability of f. So if I give an instance of the click problem to the DTM, then the DTM will transform this click instance into an independent set instance, and then will query to the function f that what is the answer of it. F will give the answer of it, and then yes, I would be able to yes then count the number of the clicks as well. Yes, this makes sense, right? Yes.
Yeah. Okay, and similarly, I mean, this also works out, but yeah, I mean, there could be cases where it gets tricky, but we'll not get into that part of it for now. Yeah, good. So, yeah. So now the question is, okay, there are there are these already hard problems here, and turns out that their counting counterparts are also sharply complete here. Okay, but could it be that there is a problem that is in P, and by that I mean it's a easy problem. Okay, something that we know is in P. Could it be that um, it go that I mean so its counting counterpart, could it be sharply complete? So something that's really easy to do in P, but can its counting version be sharply complete?
So if a problem is in P, then can it be the case that its counting version is in Sharpie? Instantly, I wanted to say no, but there cannot be. But
Hmm.
then let me think of some corner cases that
Hmm.
can this ever happen.
Hmm.
So if a decision problem is in P, then
Hmm.
then I can solve this problem in the polynomial time using the deterministic ATM, and I can count the solutions as well. But in the case of the like, I can always count that how many minimum misspelling trees are there, how many MSTs are there. I can count, or I cannot count.
There
I'm
may
not
be,
sure.
yeah,
I
exactly. There may be cases, yeah, where you cannot count.
Oh, I see.
Hmm.
I see.
So, one surprising example that is there is what is called cycle. So, cycles is the decision version of cycles is given a graph G, check whether um, set of all G such that G has a cycle. So we know that this is a very easy problem because you just do DFS or BFS, or even just check for the number of edges versus vertices. There are several ways of doing that. So if you just want to check whether there's a cycle, just do a simple check like this if it's a connected graph, or do a BFS DFS or something. So this problem is not just in P. In fact, it's one of the easiest problems that we know that are there in P. It's a linear time problem. But turns out that the problem of counting the total number of cycles is a hard problem. G comma. Okay. In fact, it is so hard that even approximating it is hard. Even approximating it to a factor of half is hard.
Yes. Now I can think of many more examples,
Hmm.
like all those problems which we used to solve through dynamic programming, like say matrix multiplication problem.
Hmm.
So in that case, we can solve that problem in off order of n cubes. However, uh, to count that how many solutions would be there would be difficult because bracketing can be done in, and the Catalan number, etc., comes into the picture. So yes, this problem is pretty good. Yeah, a problem is in P, but then it's countable.
This is known to be Sharpie complete, and also there is an approximation hardness to this. But also, one problem you might have done is counting the number of perfect matchings in a bipartite graph. Okay, so this problem is in P. Oh, sorry, checking whether there's a perfect matching is in P. Even even for non-bipartite graph for that matter, but counting the number of perfect matchings even in a bipartite graph is Sharpie complete. So the way this is shown is that we've seen this connection to the permanence problem, that the permanent exactly captures the total number of perfect matchings that are there in the bipartite graph. And this was the first problem, in fact, that was shown to be Sharpie complete. So Valiant, sometime in I think 1980s around, showed that permanent computation is a Sharpie complete problem. So, and later on, what they did was they saw that the sharp set problem reduces to permanent, and permanent reduces to sharp set, and so on. And then there were several other problems that we established to be Sharpie complete, but this was the first among the set. Okay,
What is I have a query here. So what is the relation in between then? Do we know any relation in between the P and the FP kind of the thing? Why so? Because do we have problems whose counting is easy, but then whose solution is difficult?
hmm, yeah, so that cannot happen because um, if let's say f is in fp, then what this means is I can count the number of solutions to it in polynomial time. We can find this in polytime, and now P only asks whether there is a solution. So what we can do is check if f of x is greater than 0. If it is greater than 0, that means there is at least one solution. Then we will accept. Otherwise, we will reject. So, because this is actually doing something stronger, it's not just telling us whether there is a solution, it's telling us the number of solutions.
So, but then loosely we used to say that, I mean, in case if we do not restrict ourselves only to the decision problem,
Hmm.
and the P-complexity class would also mean that all those problems which can be solved in the parameter. So, is this definition true, or there is some flaw in this definition
Uh,
that no, the problems should only belong to the decision domain only, and then only these complexity classes need that.
I did not exactly capture the question, so let
So,
me
so,
try.
so, so,
Hmm.
so, so my query is that saying that whether there exists a solution or not is one thing,
That
and
is
then
it. This
getting then or and then getting the solution is another thing, isn't it?
right, but that is not what FP is doing. Um,
Not
so,
FP, I mean to say simple P, polynomial P complexity.
P is just checking whether there is a solution. It's
So
a
is it
decision problem, so it you are only allowed to have one bit of answer output. One if I mean um, yeah, if the some question that we are asking should be always of yes no type.
so then
That's why it's a decision problem.
yes, then why do we often say so? Is this I mean
Hmm.
so rigid that this P and the NP class, I mean these complexity classes in the time domain are only restricted to the decision class problems only? And can't I say that P is the class of the problems which are solvable in the polynomial time? Usually we used to make this
It's a class
statement
of
in the algebra
it's a
analysis.
it's a class of decision problems that are solvable in polynomial time.
Oh, it cannot be any
It
problem.
cannot be any problem. Yes. Okay. Hmm. Okay. So yeah. So just to summarize, what we saw was there are indeed problems whose decision version is easy, but the version is very hard. Okay. And yeah, this is a very nice connection that uh, was done in the class, I think. So how do you interpret the number of perfect matchings as a permanent?
I don't understand what this permanent is.
Okay, so we know determinants, right? And determinants and permanents, these are very close cousins. Okay, so what does that mean? So we'll look at x1 x2 up to xn. Let's say these are the variables, and this is a n cross n matrix, boolean matrix. Okay, and this thing that we have written here, this is the adjacency matrix of the graph. Okay, I mean I've just written random values at the moment. Okay, let's not worry about the exact values. So this is the adjacency matrix. Okay, now okay, now one thing to see is what is a perfect matching. So let's say I have a bipartite graph here, x1 2 okay, let me see. mm, okay, I'll just take an easier example for now. Okay, so okay, let's look at the this particular bipartite graph, and let's count the number of perfect matchings that are here.
Yes. So then the number of the perfect matchings would be 1, 2, 4, 4 perfect
Okay,
matchings.
I'll just label this A B C D W X Y Z. Okay, so if we look at these two, okay, this is one possible matching. The other is that I can choose I can choose these two and these two, and similarly for every component, either choose the horizontal edges or choose the cross. Similarly for this, either choose the horizontal edges or choose the cross. So there are two choices for both, so there are four perfect matchings in total. So let me just write that. Okay, so A, what is the first perfect matching? That A is matched to W, B is matched to X, C is matched to Y, and W is matched to Z. Okay, so okay, I think a better way to write this would be that, let me just number these. Okay, so I'll delete this. Okay, I'll call this 1 2 3 4, and I'll call these also 1 2 3 4, but I'll just write it with a different color. Okay, these are separate vertices, these are totally 8 vertices, but think of these as a color and a label. Okay, so then what are the perfect matchings that we have? The Yeah, first one would be that the blue one is matched to a red one, the blue 2 is matched to a red 2, sorry, and 3 is matched to 3, and 4 is matched to 4. Okay, the second thing would be, this is one. Second thing would be that 1 goes to 2, 2 goes to 1, 3 goes to 3, and 4 goes to 4. I'll just write all of them. Okay, so now these are the four possible perfect matchings that we have. And what observation can we make between, so think of these as function from blue to red. Okay, so in this function what happens is the blue one goes to this, and so on. This is the mapping that we have. Okay, so what can you observe about this function? In the sense, is it a 1 1 function, is it a onto function, is it a bijection, or
So this is bisective and 1 to 1 and on to kind of the method.
exactly. So this is basically a bijection um, from 1 2 3 4 to 1 2 3 4, all of them. Okay, so that is the property of the perfect matching, because it only allows you to take one vertex to some different to some other vertex. Okay, and two vertices cannot go to the same thing, therefore it naturally captures the fact that it is a bijection. Now
In fact, this is a permutation. This is a
this is a
rearrangement and permutation.
exactly, this is a permutation. So how many permutations um, can you have from n bit?
So there would be a factorial n number of permutations.
Very good, so there would be n factorial many permutations. Okay, now what we'll do is, for each of them. So um, so let's say that pi of n, this is the set of all possible permutations that you can have. Okay, I will not get there. Okay, sorry, forget about that, I'll introduce that later. So let's say pi is some permutation from 1 to n. Okay, so and we observe that there are n factorial many permutations. Now um, now what we'll do is think of all possible um, permutations. So let's say pi is the set of all um, or I'll just call it Sn for now. Okay, we'll use the standard notation. So this is the set of all possible permutations from n bits to n bits. Okay, and um, hmm, hmm, hmm. Okay, so yeah, so I can denote the same thing. Okay, wait, just give me a second. Hmm. Hmm. Okay, I'll just need one more concept for this, which is called the sign of. So are you familiar with the sign of the permutation?
I don't know.
Okay, so sign of permutation is basically the number of inversions that we are doing. So for example, um, if uh, a larger number here gets mapped to a smaller number, for example 2 here goes to a 1 here, then um, there's an inversion that is happening.
Oh, yes, yes, I
So
understood. Like 1 to 2 is not an inversion.
exactly, so we look at the total number of inversions. If that is um, if that is even, then we will say it's an even permutation. If the total number of inversions is odd, then we will say it's an odd permutation. For example, here there are no inversions, so this is an even permutation. Okay, because 0 inversions. And okay, and here we have only one inversion, so this is odd. And then what about the other two, which is even and which is odd?
So odd. I mean, if I have odd number of the inversions, then it would be negative, is it? And even number of the inversions, then positive.
Yes.
Okay, okay. Yes. So, like in this case, I have only one inversion here. In the case C, so this is odd, and
Yes, so this is the only inversion, this is odd.
and here in this I have two inversions here in the part D, so even, right?
Yes. Okay, So um, okay. Hmm. Okay. So recall that, I mean, in the definitions that you would have seen for permanence, so sorry, for determinants, what happens is you have um, uh, these are called adjoints, right? So you um,
Yes, yes,
mm,
adjoint. So
right.
I need to use that formulas to be compared. It take the find the inverse and then adjoint of A.
Hmm.
No, inverse of A used to be the adjoint of A divided by the determinant. Something used to be
Yeah,
like that.
yeah. So there's an equivalent way of writing this in terms of permutations. So I'll just give me a second. Okay, I just want to make sure what I have in mind. So I want to write the determinant in terms of these signs and these permutations. So let's say A is the matrix that we have. Okay, just a second. Okay, I'm just trying to arrive at it and I will explain. So hmm, okay. Hmm. Okay. Yeah, I'll just explain this now. Okay. So look at this matrix that we had x1 to xn and x1 to xn, and we have all possible 0, I mean, some 0 1 values here. Okay. And now what, I mean, we will part by part uh, I mean, define this. Okay, so what does this part denote? So what is pi of I nen x I comma sigma I? So notice that sigma, so Sn is the set of all possible permutation. We said there are n factorial many permutation. Sigma is one such permutation. So sigma is a permutation from n to n. Okay, so what it does is you have 1 2 3 4 and so on. It's going to give some ordering to them. Okay, some kind of a mapping, maintaining that it's a permutation. Now uh, what does this denote? So basically this is denoting that 1 goes to 1 here goes to sigma of 1, which is 2. Okay, 2 here goes to uh, 2 here goes to sigma of 1, sorry, sigma of 2, which is 1. And so let me just write this in terms of xi. So what does this denote? x1 comma 2, then x2 comma 1. Okay, and let's say that this particular this particular permutation is just flipping uh, the previous and next entries. Okay, so this is 2 1 4 3 6 5 and so on. Okay, then what will this look like? Sorry, I'll just write this cleanly. Okay, let me just do this again. So what is the permutation sigma that we have? The permutation sigma is 1 2 3 4 5 6 and 4 5. Okay, let's say this is the particular sigma about which we are talking. Then we want to write this particular expression. What is that? So x of 1 comma sigma of 1, which is 3, times x of 2 comma 2, because sigma of 2 is 2. Can you just tell me the rest of
Yes,
this?
yes. So remaining would be x31, and then x46, and x54, and then x65.
Oh, great. So what we are saying is that for every permutation sigma, you can write an expression like this. Okay, and why are we writing it like this? Because it tells you what entry to look at. So I should have just numbered it 1 2, and that would have been easier. Okay, so when I say x13, what I mean is what is the entry of first row and the third column. So this variable xij represents the value of the matrix at ij.
Yes.
Okay, so okay, so what's really happening when we do the permutations in terms of um, the earlier definitions that you might have seen is that you look at the first value a11 and then compute the adjoint, and then you have a12 and you compute the adjoint, and so on, right? So what really happened when you, for example, computed this value, uh, this this thing is, when you multiply it with a11, you sort of leave out these two columns and then only look at n minus 1 cross n minus 1 thing. Okay,
Yes, yes.
so why is that happening? Because we are looking for a bijection, because the first row is already mapped to the first column. They cannot participate in the permutation. The rest of the permutation is only happening between these people. Okay, so that is basically what is happening. You are actually going through uh, all possible permutations, and we are writing those values in terms of multiplication, and then there's a sign that is associated with it. So it turns out that the sign that you compute is actually the same as, so this is there's a proof for this. The sign that you write in the determinants is actually the sign uh, of the permutation. So for example, we had this particular permutation here, and we had a term corresponding to it. So what will be the sign of it? So what will really happen is you have all possible uh, terms like this, all possible monomials. So x11, x12, x13, x16, then you have x12, x21, sorry, x34, so on. You have all possible n factorial many um, terms like this, and notice that these are values, right? Because each of them is a 0 1 value. Xij is just a entry in the matrix, and we are going to multiply all of them. Okay, so this will just be either a 0 or a 1. So you have all these monomials here that evaluate to 0 or a 1, and we're going to do some arithmetic operation on them. So whether to add them or whether to uh, subtract them, how do we determine that? We will look at the permutation. So let's say this is the permutation that we looked at. We will find its sign. Sign is nothing but the number of inversions. So sign of sigma is nothing but is 1 if sigma has odd sigma has even number of permutations, and it is a minus 1 if there are odd number of permutations. So each term corresponds to a permutation. If the sign associated with it is a plus, then we write a plus here. If the sign associated with it is a minus, then we write a minus 1 times the monomial. So just to summarize what we did, we looked at all possible permutation sigma. Okay, for each of them we calculated this expression in terms of xi's. So xi comma sigma I, and we multiplied all of them. That gave us this term x11, x12, and so on. And then there is some sign that is associated with each of them, each permutation sigma. That is something we are going to multiply with this value. Okay, and at the end just sum all of them together. So that exactly corresponds to the determinant of A.
Yes. Uh, so, but then I could understand this thing that we are taking this product and then a permutation is giving to us, and from that permutation we can find out the sign as well depending upon the number of the inversions, and we carry out this sum for, and summation is being carried out over sigma or over I, what,
Over sigma, yeah.
to the sigma, right? To the sigma. It's okay. And how do we get this sigma then? How do we get, this permutation for any given matrix? For any given
You will
matrix,
you
yes.
will go through all possible permutations. So there are n factorial many of them. We will go through all of them.
But then, like when we compute the determinant of a matrix,
Hmm.
do we really take all permutations into consideration?
Yes. So, um, yeah. So that's what I was saying. So when you do A11 and followed by A11, what happened is we decided that 1 will map to a 1.
But then, because say if we view this adjoint A11
Hmm.
as a permutation,
Hmm.
so like say can we draw a square matrix and having some elements, so that I can pose my question. Like say can we draw a
Okay. Yes. Yes.
matrix
yes. Good.
of
Yeah.
some dimension,
So
say 4
yeah,
into 4 kind of thing.
2 by 2,
4 into 4,
4,
something 4 into 4, yeah, that would be then to
4
the
by 4.
permutation. 4
Okay.
into 4, yeah.
Okay.
And
So what are the values?
so like say you can write here say A11 like this, no issues. A11, then
Okay.
A12, uh, and then A13, and then A14, and then A21, and then A22, A23, A24, and then so on. So, like
Hmm.
um, with these elements, I would be having 24 number of the permutations possible with 4 number of the elements.
Hmm.
And if I take the value of A11 and if I find the adjoint of the remaining stuff, so that would be 3 cross 3 matrix. So then, and then A12, I take A12 and then again 3 cross 3.
Hmm.
So then basically 4 into, so how many calculations have been made? 4 into, and then 3 adjoint matrices.
Hmm.
And so, how many permutations are there in the three adjoint matrices? Because for a matrix having say 4 elements, a
Hmm.
matrix having dimension of 2 cross 2,
Hmm.
uh, we know its value. Its value is just take the cross,
Hmm.
right? And then, so are we really?
Okay.
Are we,
Let's go from smaller number to bigger number. Let's say if it's 2 by 2.
or even if it is just one value, then what is the value of the determinant? The value itself.
The values.
Itself, right? So for one element, the solution the one, and it's okay, same as the permutation.
Hmm.
And then if I have two elements,
Two
say A1,
elements. Hmm.
A11, and then A12, and then A21, and then A22. Its determinant is equal to A11, A22, and then minus A21 and A12.
Because there are only two. Um. Huh. Because there are only, sorry. What am I? A12, A21. Okay. Because there are only two permutations that you can imagine from 1 to 2. That's either 1 to 2 or 2 to 1.
So where do we get this fact reflected in this calculation?
Hmm.
A11,
So,
A12.
hmm. So Sn will be these two permutations.
Yeah.
Okay. And now let's say we will take the first permutation, which is 1 goes to 1 and 2 goes to 2. Then what is the sign of this permutation? The sign is 1 because there are no inversions.
Yes.
So this is a plus. And what are these terms? 1 goes to 1, and I'll just write it A then so that we are consistent. Okay? 1 goes to 1 and 2 goes to 2. Then we will look at the second permutation, which is 2 goes to 1.
Yes.
Okay? So what is the sign of this?
Its sign would be negative. There is
Negative.
there is one
There is
inversion.
one inversion here. So minus 1 goes to 2 and 2 goes to 1, which is exactly what we have here.
Oh, this process is really wonderful. Yeah. Yeah. So if we go for this three by three
Let's
also,
do
then
3
we
by
can
3.
calculate.
Hmm.
Yeah. I understood.
Hmm.
I understood. Yes, yeah, I understood.
Actually, there's a very nice way of exactly showing. I remember when I was taught this, it was like it was two things side by side, two definitions, and it was very obvious that these are two, both of them are capturing the same thing, but I don't fully recall it. But if I do, I'll share it with you. Okay. So yeah.
Sure, sure.
Okay. And then what about permanent? Permanent is exactly same as determinant, but forget about the sign. Okay, just add them blindly.
So is this idea of permanent or this way of computing the determinant, is this valid only for the Boolean
Boolean
matrix, or
matrix. Okay.
is this valid for every, I mean, for all kind of the matrices?
Because um, yeah, the kind of things that we did here, no, we did not assume the values here. I mean, we didn't say that this should be Boolean.
So
So
this
this is
formula
a
which you got,
general.
it is a general one or only for the Boolean?
Yeah, this is a general one because we did not assume the fact that these are booleans. As of now, we haven't used.
Yes.
Okay. Yeah. Hmm. Okay. So permanence is basically the same as determinants, only without the sign. But if you think of it as a computational problem, for example, I give you a matrix, and you want to compute a determinant of it. So can you do this in polynomial time?
So what's the question? What's the query?
Uh, the input that I'm giving to you is this matrix, n
Yes.
cross n matrix, and you want to compute the determinant,
Yes.
or think of it even as a decision problem. I'll give you a matrix, comma, some answer. You have to check whether the determinant is equal to that answer.
Okay. Okay. So, but then determinants, I guess, do not have uh, polynomial complexity.
Yeah,
Do not have
you do.
determining determinants. Do not have polynomial complexity.
Actually, you do have efficient algorithms for determinant. So you uh, so there are efficient ways of doing some uh, um, operations to the matrix, bringing it into Gaussian and so on, so that the calculation becomes easier. So there are actually very efficient. Um, is it n to the 4 or something? So anyway, there are efficient deterministic polytime algorithms for computing determinants. Okay. mm, I don't recall at the moment, but if you google it you will get it. Okay. So okay, but it turns out that permanent computation is very hard. So although they are very close cousins, they look they look the same, only that permanence does not have signs, it's just addition. But computing permanence is very hard. So this is so hard that it's complete for Sharpie. Okay.
Okay.
Um,
And why so just by ignoring, because if I can compute all other values, then it is just a matter of putting a sign
Hmm.
and nothing
But the we can't. So the algorithm for determinant does not go like this, because how many permutations are there? There are n factorial many permutations. This is already exponential, and we can't afford to calculate all of them explicitly. Okay, so there is something cleverer that it does. If we do the naive strategy of, calculating all the values and doing, the number of terms itself is so large that we can't afford to do this in polynomial time. So there are different algorithms that use different properties about it to come up with the value of determinants, and the sign mysteriously plays a role in making it easy.
else. But then this gives rise to something else, that if the factorial of n number can be avoided, then probably the factorial of n can be avoided at many places. Like this factorial of n can be avoided in determining the determinant of the matrix, then can this also be avoided in the traveling salesman problem? Because if we can find an efficient deterministic polytime solution to compute the determinant, and if the determinant has been posed into a problem wherein the calculation of factorial of n is mandatory, and somehow if we could avoid the calculation of the factorial of n and come up with a polytime algorithm,
Hmm.
then why can't we do the same thing for the other problems as well, and wherein this factorial of n calculation is required, like the traveling salesman problem?
Hmm. Because the signs here are not arbitrary. Okay, so these are controlled by what the permutation is. So for the fixed monomial, the signs are already fixed. So I think the answer to that really lies in what kind of efficient algorithms we have and why it works. So if we know that, we can ask, okay, where all will this work? Like if this were some other function instead of being attached to the sigma, will the same algorithm work? Because I don't have this algorithm fresh in my mind, I can't answer why that will not work. But notice that this is not arbitrary. Okay, this is tied to sigma.
But then even if yes, this is the sign depends on the permutation,
Hmm.
it's okay. But then permutation would be something which is finite. Could be very large,
What do you
but
mean?
then this would
Huh.
be finite.
Right,
Finite in the sense
right.
that
Huh.
we are so for a permutation, if the set has got n number of the elements, then even though there would be factorial n number of the permutations, but I just need to compare n number of the elements. I mean, in one go. I mean, at a point, at
At
any
a
point of
point.
the time, I just need to compare the n number of the values to know to count the number of the inversions. And I'm not sure,
True.
but then this counting of the inversions can be done efficiently by using the divide and conquer philosophy in some log time, some n log n time, I guess.
True, true.
Uh,
The computation of sigma is not really bothering us, because you can always do this in polynomial time, right? Just uh, yeah, I mean, just look at the permutation you have, keep on adding if you see an inversion, because it's a local thing, no? Like, look at the current index, look at the mapping. If you see uh, like a larger value mapped to a smaller value, then increase the count and go ahead. So this is a very linear sort of thing. Just keep scanning and keep adding. So
yes.
computing sigma of n is not really a problem. But what I'm saying is that um, the fact that these are very, alternate, plus minus alternations, does play a role in. So for example, if I look at two terms, a11, um, okay, just um, a21, oh, this is really okay, sorry. I'll just take a small example. 1 goes to 2, 2 goes to 1, 3 goes to 4, and 4 goes to 3, versus 8 goes to 1, 1 goes to 2, 2 goes to 1, 3 goes to 3, and 4 goes to 4. How many inversions are there? So there is only one swap. So earlier 3 was mapped to 4, 4 was mapped to 3, and now we have just changed it. Okay, so
Yes. 4,
so
3 and yes, right.
so one of them has an odd, this has an odd sign, because this is the inversion that we have, whereas this has an even sign, because you'll see two inversions, one here and one here. Okay, so imagine that you have two very very large, although this is a small example, imagine you have two lot of like n permutations of length n, where they are same everywhere except that there is one swap happening. Let's say in the first one 3 goes to 4, 4 goes to 3, and here 3 goes to 3, 4 goes to 4, everything else is the same. Then um, what's really happening is you can uh, I mean, you know that one of them is going to have a negative sign, so I don't really need to calculate the rest of the product, right? I mean, just keep this part separate and then calculate the rest of the product separately, and then I'm just gonna have to subtract these two. Okay, so the fact that sigma has this nice property that uh, if you make one swap, then the signs are going to change. Okay, uh,
I understood this thing. This is related to the idea of cycles. Like say if I've been given n number of the element and just two elements are getting swapped. One is mapping to two and two is mapping to one, and the remaining elements are mapping to themselves.
hmm,
So then I can write such a permutation as by just one cycle, say A12. That's one two cycle only.
hmm,
And yes, and there used to be a theorem as well that every cycle can be represented as a product of the two cycles.
transpositions, yes.
Yes.
So okay, so I mean, I can't, okay, the only one intuition I have for this is that the fact that there are, exactly half pluses and half minuses, and the fact that they behave nicely, that if you just look at one swap, the rest of the computation need not be done. So these kinds of behaviors lead to the fact that we have algorithms. But why this works, I mean, the answer really lies into the algorithm, which I don't recall at the moment. But if you look at some other function where this is not tied to it, okay, so there's some other function that you have, so these properties may not be preserved. So now the kind of parallelism that we could achieve may not be achievable there. So, but I mean, that's a very very high level thing that I believe is why this works. But I really need to look into algorithm to um,
Yes, yes,
yeah.
and this permanent is hard, and this is hard. So, but then what connection it has with that problem, that
Bipartite
matching
matching,
thing? Right?
yes. So
Yes.
this is a very very nice connection. So if you look at the matchings that we drew, okay, look at the adjacency matrix of this. Okay, so let me just draw the adjacency for this. So this is the graph we had, 1 2 1 2 3 4 3 4, and you have 1 2 3 4. Okay, so if there's an edge from 1 to 1, then write a 1. Then 1 to 2 is an edge, 1 to 3 no. Similarly 1 1 0 0 0 0 0 0 1 1 1 1. Okay, this is the adjacency matrix for the graph G. Okay, Now we will look at arbitrary permutations. Okay, so let's say we wrote these terms, no, 1 goes to 1. Just let's take some permutations. This is the identity permutation. Let's look at x12, x21, x34, x43. So how many such permutations we will have? 4 factorial.
24.
So what does the permanent say? Permanent just says that calculate these values. I think it's better I write a here maybe. So because we are actually looking at the value of the matrix. Okay, what does the permanent say? Permanent says that just find all these values and sum up them.
Can you show the formula to compute permanent actually? You wrote somewhere.
Yeah, I'm just writing that. Okay, pi of x, I'll write a here, a I comma sigma I n. Okay, let's not look at this right now. Okay, just observe one thing. If okay, let's just calculate these two first and then we will observe. Okay, so let's calculate the value of this.
So this value came out to be A11 and then into A22. The
This
value
is
is A11 and A22 is 1. And then because A33
0.
also a 1. A33 has become a 1 here in this
A33 has become a 1 here, yeah.
and
Right.
then moreover A44 is also a 1,
Is
so
also
finally it came out to be 1.
to be
And
1.
moreover in these 24 numbers, wherever we find a value 0, and
Hmm.
that thing is going to become a 0, isn't it?
Yes.
Now for the second one, A12 is a 1, A21 is a 1, right? A34 is a 1, A43. So this is also 1.
A 1. So what does this correspond to in the graph? So what that means is A1 is matched to this one, 2 goes here, 3 goes here, and 4 goes here. So this gives me one perfect matching. Okay, and the it evaluates to 1. Now if you look at this, I'll draw this in red. 1 goes to 2, 2 goes to 1, 3 goes to 3, and sorry, 3 goes to 4, 4 goes to 3. This also is a perfect matching, and this expression evaluates to a 1. Now let's say I'll take one more example. Let's say I take A13, A24, A31, sorry, yeah, is the screen visible now?
Yes, yes, yes.
Okay, so then let's say A31 and A4, 4, yeah, no, 2. Okay, this is a permutation. Now let's calculate the value of this. So like you said, if any one of them is a 0, in this case A13 is a 0, then this is going to be a 0. What does that correspond to in the graph? It says A1 to 3, but there is no edge here, so this is not even a matching.
Right.
So what's really happening is, whenever you have a perfect matching, this term is going to be 1, because this is a bijection, right? I mean, if it's a perfect matching, then you exactly get a permutation on the vertices.
Yeah, I
And
understood that this perfect matching is modeled as this permanent, and this permanent to calculate the permanent is very very hard. So therefore, this getting this permanent matching is also very hard. Count of the permanent matching is very
count
hard.
of
However, yeah, I mean count of the but then getting a permanent matching is can be done in the polynomial time. Right? Yes.
yes, but this connection is something that I really like, because on one hand you have some algebraic object permutations and stuff, and on the other hand you have this matching, and this connection is very simple, but it's also very interesting.
So the people who work in the area of the algebraic graph theory study that thing wherein they have graph object on one side and they have matrix on one side and the graph on the other side. Like they used to model the Laplacian matrix, I
Mm.
remember. So uh, here also they must be having some connection in
Hmm.
between those two.
Okay. And yeah, I'm not aware of the contents of the next week, but we'll meet on Saturday, same time, 10 a.m.
There is a small request. Actually, all of a sudden, I got engaged from 10:30 to 12 on Saturday. So any time before 10:30 would be absolutely fine with me. Any time post 12 would also be fine with me. Just this 10:30 to 12 is the issue actually. Uh,
Okay, 1 second.